this second chapter of trigonometry, we were going to be extending our knowledge of the trig functions. In this lesson, we will be looking at the Pythagorean identities.
Now we're going to step it up a little bit. We're going to take a look at some slightly more complicated identities here. And we're going to do this by first of all considering the unit circle. Now remember, the definition or the equation of the unit circle is x squared plus y squared is equal to 1. Now, we've been trying for several different questions here to emphasize the connection that you should be building here between cosine and the x coordinate, sine and the y coordinate. Okay, on the unit circle, okay, when you've got a point on the unit circle, the x coordinate is the cosine of this angle, the y coordinate is the sine of this angle. And so I can replace x with cosine and sine with and the y with a sine of that angle, and we get this identity right here, which we call a Pythagorean identity or a Pythagorean identity, depending on how you want to pronounce it. Okay, so here we go. Cosine squared of x plus sine squared of x is equal to 1. Now, that identity is extraordinarily useful, and in many cases here, this kind of identity is one of the first ones you should be looking at now when you start working with identities. Now there are other versions of this, and I'll zoom in on this. If you took the original identity, cosine squared plus sine squared is equal to 1, if I was to divide everything through here by sine squared, cosine divided by sine gets you cotangent. This becomes cotangent squared. Sine squared divided by sine squared would be 1. 1 divided by sine squared is cosecant. Here's another Pythagorean identity. If I now took this and divided everything by cosine, cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tangent squared. And 1 divided by the cosine squared is secant squared. So here's another Pythagorean identity. So here are three different identities that are extremely useful. And oftentimes you should be looking specifically for these guys first before you convert everything into sine and cosine. Okay, it's often easier if you simplify it using these identities first than it is to just immediately go in terms of sine and cosine. Now, bear in mind that if these are true, other things are also true. For example, if this is true, we also know that the cosine squared of x is going to equal 1 minus the sine squared of x. Okay, that 1 from here, for example, 1 is going to equal to the cosecant squared of x minus the cotangent squared of x. In other words, I want you to know that you can manipulate these equations algebraically and they still stay equal. Okay, they remain identities. You don't always have to see them exactly like this to make the substitution. You can manipulate it a little bit to find the specific expression that you need.
Simplify each of the following. Look for Pythagorean identities. 1 plus cotangent of x squared divided by the cotangent of x squared.
All right, I'm going to do this one in two different ways. First of all, I notice that there is a 1 plus cotangent squared in the numerator, and I know, based on what I've just seen, that that is going to be the same as the cosecant squared of x over the cotangent squared of x. Now, in this case right here, I want to take this as far as I can. I want to simplify this as far as I can. There's not a whole lot I can do here. But what I know here is that cosecant is like 1 over the sine squared of theta. Cotangent is going to be cosine squared of theta over the sine squared of theta. Can you see that? Nope. And when I've got fraction divided by fraction, okay, what I can do here is multiply by the reciprocal. So this will become 1 over sine squared of theta multiplied by the sine squared of theta over the cosine squared of theta. I reciprocate the divisor there. Sine squareds will cancel, and we're going to get that this is 1 over cosine, or this is going to be secant squared. Okay, this will be equal to secant squared. Now, bear in mind that there are some restrictions here. Okay, I've got a cotangent here, and so we would be getting here that theta can't be equal to multiples of pi. Okay. Additionally, I've got a cotangent in the denominator, which means that cosine can't go to 0, in which case we would also get that you can't have pi over 2 plus n pi, where n is an element of the integers. So there are some restrictions there that we need to identify here. Now, there is another way of doing this though. I could have, for example, actually maybe I'll do it up here, or I could have seen this as a binomial divided by a monomial and done 1 over cotangent squared plus cotangent squared over cotangent squared. Now, 1 over cotangent squared, remember that cotangent is the reciprocal of tangent. And so that would get you tangent squared of x, and cotangent over cotangent is just going to be 1. And then when I look at my identities up top there, I know that tan squared of x plus 1 is going to be the same as the secant squared of x, which is exactly what I found down here. So it doesn't really matter how I approach that, I'm going to get the same result in the end anyway. Oh, I just noticed that I accidentally switched variables here. Sorry, I should have been in x the whole time, not changing it to theta. Oops.
Sine squared of x plus sine squared of x multiplied by the cotangent squared of x.
So for this question right here, when I look at it, first thing I notice is that I don't actually see a Pythagorean identity the way I want it, okay? There is no identity that really deals with it like this, so I can't do that substitution right away. Then I start to look at this and say, well, is there any kind of obvious algebra that I can do that would make this a little bit easier? And notice that I've got a common sine squared to both of those terms. So I can factor out that sine squared, and then I'm left with 1 plus cotangent squared. Now I go back and I think, okay, now do I see a Pythagorean identity? And yes, I do. Yes, I do. The 1 plus cotangent squared is the same as the cosecant squared. Now, remember, cosecant is the reciprocal of sine. So this is, sine squared of x multiplied by 1 over the sine squared of x. Those are going to cancel. I'm just going to get 1. Now, those are going to cancel so long as I identify my restriction, and I've got cotangent here, and that tells me that x cannot equal multiples of pi, where n is an element of the integers. So that's true so long as that's true.
Sine squared of x divided by the cosine squared of x plus the sine of x multiplied by the cosecant of x.
Okay, so this question's in some ways similar to the one that we just did. Notice that I don't see any Pythagorean identities popping out right away here. However, there are some obvious changes that can be made here. So for example, sine squared over cosine squared is actually equal to tangent squared. Now, I know that oftentimes what you're told to do is immediately put things in terms of sine and cosine. But when I'm looking for the Pythagorean identities, which is the first thing I should really be doing in most of these cases, in this case here, that's not what I want. Now watch this. What's sine of x times the cosecant of x? Well, cosecant is 1 over sine. So I've got sine over sine. Well, that's just 1. Now, granted, that is so long as x does not equal n times pi, where n is an element of the integers. Okay? Because there's a restriction there. I can't cancel that there. Now, tangent squared plus 1 is equal to secant squared. That's the Pythagorean identity that I was looking for. And so now, and I got this tangent squared here. Tangent comes with its own little set of restrictions here. X can also not equal pi over 2 plus n pi, where n is an element of the integer. So there's a few restrictions here, or a couple restrictions, but that's the final answer that we get to. That's the one we're looking for.
The secant squared of x minus 1 divided by the sine squared of x.
Okay, now in this case, the Pythagorean identity kind of jumps right out at you. Secant squared minus 1, well, that is going to be equal to tangent squared. Okay, now that's not obviously what the identity is. What you got to do is you got to manipulate it a little bit. You just got to subtract the 1 over sine squared of x. Now, this is going to be the same as, well, tangent is the sine squared of x over the cosine squared of x, and I'm dividing by sine squared. I'm multiplying by 1 over sine squared of x. Notice that those two will cancel, and I'm left with 1 over cosine squared, which is just secant squared of x. Now, this is true as long as we identify the restrictions. Sorry, I'm seeing a secant here, and the restriction for secant is that x cannot equal pi over 2 plus n pi, where n is an element of the integers. Okay? Yeah. That's the restriction there. Notice I've also got a sign in the denominator, and sign doesn't, goes to 0 when x is equal to pi, multiples of pi. So what we're getting here is this two sets of restrictions here, one from that secant, one from that sign in the denominator. And there you go. So that's true. It equals secant squared so long as this is true.
The sine of theta divided by 1 plus the cosine of theta plus the cotangent of theta.
All right, this is a great little question. Notice that there's no Pythagorean identity here, okay? But there is some obvious algebra that I could do because I've got two separate terms here. I'd kind of like this to be one term. So this is the sine of theta over 1 plus the cosine of theta. Whoops, sorry, not equals, plus cotangent. And cotangent is going to be cosine of theta over the sine of theta. Okay, now I'll deal with some restrictions here in just a second. Notice that my common denominator here will be just the product of those two. So this is going to be sine of theta times 1 plus the cosine of theta. I'm not so worried about expanding the denominator. I am about the numerator here. So sine times sine will give me sine squared of theta. And then when I distribute this through, I'm going to get cos theta plus the cosine squared of theta. Now, sine squared and cosine squared, when I add those together, I'm going to get 1. That's the Pythagorean identity. And then I get 1 plus the cosine of theta in the numerator over sine of theta times 1 plus the cosine of theta. And oh, notice that those are the same too. So I'm left with 1 over the sine of theta, which is the same as the cosecant of theta. And now I want to talk about the restrictions. Okay, notice I had a sign in the denominator. Now a sign in the denominator tells me that I cannot let x equal multiples of pi. But additionally, I had this 1 plus cosine in the denominator, which means I can't allow cosine to go to -1. Let's just think about it. I can't allow cosine to go to -1. Where does cosine go to -1? Well, it goes to -1 at pi. Oh, I've already got that in there. So that restriction that I got from sine actually covers me for both of those different possibilities.
The cosine squared of x minus 1 divided by the tangent of x.
Okay, now in this case right here, I'm seeing something that looks like that original Pythagorean identity, that cos squared plus sine squared equals 1, but it's not. It's cosine of x squared minus 1. Now what they've done is they've brought the 1 over, brought the sine over, and so it turns out that numerator is actually equal to the negative sine squared of theta over the, theta x over the tangent of x. Okay, now to simplify this even further, I'm going to take that tangent and write it as the sine of x over the cosine of x. And now that's going to become the negative sine squared of x. I'm dividing by a fraction, so I'll multiply by the reciprocal, cosine of x over the sine of x. Notice that one of the sines will cancel, and I'm going to be left with negative sine of x times the cosine of x. Okay? Now, sine will cancel so long as it doesn't go to 0, which means x cannot equal n pi, where n is an element of the integers. Now that's because of the sign that's canceling. But again, notice because we've got a tangent in there, that I'm not going to be allowed to equal pi over 2 plus n pi as well, where n is an element of the integers. And so those are the restrictions. Notice that these are coming up quite a bit. When there's a restriction, that seems to be frequently what the restrictions are.
Prove each of the following identities. The secant of x minus the cosine of x is equal to the sine of x times the tangent of x. Okay. Now, to prove an identity is in some ways similar to what we were talking about when we were talking about verifying an identity. And by that I mean, I don't know that these are equal. So I am going to work on the left-hand side and the right-hand side of this expression independent of each other. But what I want to do is I want to show that the left-hand side and the right-hand side are actually equivalent to the same thing. That's kind of what I did with verifying, except with verifying I plugged in a number and showed that I could evaluate them and get the same result. I'm not going to do that here. What we're going to do here is we're going to use what these things are equal to. Now, when I take a quick look at this, on the left-hand side here, I notice I've got two terms. On the right-hand side, I've got really one term. It's got two factors, but just one term. I'm going to try to put these together, but to do that, I'm going to need to identify the denominator. So
I know that that step right there is equal to this step right here. My common denominator is going to have to be cosine of x. Okay? And actually, when I think about what's going on over here, you know what? I'm going to play a little bit with this as well. This is going to be sine of x because right here I've pulled out a cosine of x in the denominator. And I know that tangent, when I write it in terms of sine and cosine, is going to put a cosine in the denominator. Okay, so I'm kind of jumping back and forth here. I'm not moving stuff across. I'm playing on one side and the other here. Now, on this side right here, that's going to end up being 1 minus the cosine squared of x, because I'm going to have to multiply numerator and denominator by the cosine of x here to get common denominators. Okay. On this side right here, I'm going to have sine of x times the sine of x. Okay, that's going to be sine squared of x. Whoops. So I wrote that kind of funny. That is going to end up being the sine squared of x over the cosine of x. Okay, now I've put those together into one term. I've added the fractions. Okay, in other words, I've done the algebra. Now I'm going to look at it again, and I'm always looking for Pythagorean identities first, and I see it right here. 1 minus cosine squared is the sine squared of x. And now look what I've been able to do. I've been able to show that independent of each other, these two sides were both equal to sine squared of x over the cosine squared of x. I know that this is equal. Okay, good.
The sine of x multiplied by the cosine squared of x plus the sine cubed of x is equal to 1 over the cosecant of x.
Okay, so once again, what we're going to do to prove this identity is we're going to split this up, and we're going to show that independent of each other, these two sides of this expression here, equation here, are equal. Now, I'm obviously going to spend the most of my time working on the left-hand side because there's far more going on here. However, I'm going to start on the right-hand side because look at this. I've got 1 over the cosecant of x. Well, I know that cosecant is the reciprocal of sine. So if I'm reciprocating that, that is just going to spit a sine out. Now that is probably a simpler form that's easier to work with here. So the first thing I'm going to look for here are Pythagorean identities. And although it kind of looks like they might be there, there's nothing there that exactly fits the form I'm looking for. So I'm going to look, I notice I've got 2 terms here. So I'm going to assume that there might be some algebra that I can do. And it turns out, yeah, there is, because there's a common factor of a sine there that I can take out. So this is going to be equal to the sine of x times cosine squared of x plus the sine squared of x. Oh, and that was a huge step forward because now I do see a Pythagorean identity in there. Cos squared plus sine squared is 1. 1 times the sine of x is the sine of x. And there it is. I've been able to show that the left side and the right side are equal to the same thing.
The secant squared of x divided by the secant squared of x minus 1 is equal to the cosecant squared of x.
All right, one more. Here we go. So we're going to split this up, left side and right side. Now, obviously, the work has got to be done on the left-hand side because this is where most of the material is that I have to work with. And I'm looking for Pythagorean identities first. And I see one in the denominator. Okay, so this is going to be secant squared of x over, that denominator becomes the tangent squared of x. Okay, awesome. Now, I want this to eventually look like a cosecant. Okay, I'm going to have to play with this a little bit. And, you know, this is one of those times here where it probably makes sense for me to now write this in terms of sine and cosine. So, secant is 1 over cosine. Sine squared over cosine squared is tangent. Now I'm dividing fractions here, so I'm going to multiply by the reciprocal. So 1 over the cosine squared of x times the reciprocal, cosine squared of x over the sine squared of x. And there we go, because my cosines will cancel, and I've got 1 over sine squared. Well, I know what that is. That's cosecant squared. And so there we go. The left-hand side and the right-hand side are equal to each other, independent of each other.
The sine of x plus the cosine of x squared is equal to 1 plus 2 times the sine of x times the cosine of x.
Okay, here comes another one. Now, again, I'm going to do this separately. Okay, I'm not going to work from one side to the other here. I take a look at this, and now do you see any Pythagorean identities to start off with? No, I don't. But I do see some obvious algebra here, at least, or there's something here that suggests an algebraic step that I should take. Sine of x plus cosine of x is being squared here. So this is the sine of x plus the cosine of x times the sine of x plus the cosine of x. Whoops, running over there. And when I distribute that out, I am going to get sine squared of x plus 2 sine x cos x, which is exactly what I'm seeing over there, plus the cosine squared of x. Now, do I see any Pythagorean identities? Yes, I do. Sine squared and cosine squared together become 1. So that's 1 plus 2 sine x cos x. But that's exactly what was on the other side of the equation. So yeah, I've been able to show that, again, independent of each other, the two sides of this expression are equal to the same thing.
The sine of theta divided by 1 plus the cosine of theta plus 1 plus the cosine of theta divided by the sine of theta is equal to 2 times the cosecant of theta.
Okay, so this one's a little bit more involved, but that's okay. Notice that the right-hand side, there's not much to work with, but on the left-hand side, there's plenty. There's no Pythagorean identities that I see right now, but I do know that I've got 2 terms here, 1 term here, so I'm going to be adding these together. And so I'm going to get a common denominator. It's going to be 1 plus the cosine of theta times the sine of theta. Now, that means I multiplied numerator and denominator here by the sine of theta, so that's going to get me sine squared of theta. And then I had to multiply this numerator by 1 plus cos theta, and when I expand that out, I'm going to get 1 plus 2 cos theta plus cosine, squared of theta. Okay, I ran over a little bit, but that's okay. Now I do see a Pythagorean identity. I see sine squared and cos squared. That's my 1 plus 2 cosine of theta. That's what's left over in the numerator. 1 plus cos theta times the sine of theta. Now, this is going to end up being, if I add those two 1's together, in the numerator, look, I'm getting 2 plus 2 cos theta over 1 plus cos theta times the sine of theta. And notice what I can do here. I can take out a 2, and I'm left with 1 plus the cosine of theta, all over 1 plus the cosine of theta times the sine of theta. And hopefully you're seeing where we're going here. 1 plus cos theta over 1 plus cos theta, they're going to cancel. I'm left with a 2 in the numerator, sine in the denominator. That is the same as 2 cosecant of theta. That was what the right-hand side was equal to. It took me a while, but I was able to get the left-hand side to look like the right-hand side, and once again, independent of each other.
The secant of theta divided by the tangent of theta plus the cotangent of theta is equal to the sine of theta.
Okay, here's another one that's going to have a little bit more work to it, but that's okay. I'm obviously going to work on the left-hand side. That really can't do anything to the right-hand side. That's perfect. It's beautiful. Now, I don't see any Pythagorean identities here, okay? But I do see fractions in the denominator. Now, actually, I see fractions everywhere because secant is 1 over the cosine of x. Tangent is the sine of x over the cosine of x. Cotangent is the cosine of x over the sine of x. So I see lots of fractions here. What I'm going to do is add those two fractions in the denominator. Whoops, sorry, I want you to be able to see it when I work on it. So I'm going to get 1 over the cosine of x. Now down here, my common denominator is going to be cos x sine x. I'm going to multiply them together. But if I do that, here I'm going to get sine squared of x because I have to multiply numerator and denominator by sine x. Over here I'm going to get the cosine squared of x. Okay? Sine squared plus cos squared. There's the Pythagorean identity that I was looking for. This is going to be 1 over the cosine of x sine of x. So, whoops, sorry, there you go. Now I'm very, very close to my answer here. I've got a fraction divided by a fraction. So I'm going to multiply by the reciprocal. So cos x sine x over 1. And now notice cos over cos cancels, and I have finally worked this down to that simple expression sine x, which is the same on the right-hand side. So we've proved this identity.